Hello and welcome to the States of Matter lecture. This is the second and last lecture in the Properties of Matter series of lectures. Hopefully this is a review for all of you guys. Hopefully you already know your states of matter, so let's get started. The state of matter, what is the definition? It is the physical, it's the physical form in which all matter naturally exists on Earth. Look at this word right here, physical form. This is important. We're going to see it just right here in just a second. Your states of matter are most commonly your solids, your liquids, and your gases. There is another, and I believe there actually is another one after that. But we usually talk about solids, liquids, and gases. Anytime, remember I mentioned physical form in which all matter naturally exists on Earth, and do you remember how during the last lecture we were talking about physical and chemical properties and changes? Well, anytime you're talking about a state of matter, we're talking about a physical state, therefore it is a physical property. Anytime you're talking about a change in a phase or state of matter, it is a physical change. That is important for you to know, but it's also important for you to know on a test or a quiz. So any kind of change involving liquid to gas, melting, boiling, anything like that, that is a physical change. And how do you tell ultimately whether something is a solid, a liquid, or a gas? You can tell it's distinguished by the way that it fills up a container. This is, we're going to talk a lot more about that here in just a few minutes. Keep in mind as we go through the states of matter that all matter is made up of little particles, and those little particles are always moving. Even in solid form, you may not think of them as moving, but they are. They just don't have a lot of room to move. They're sitting there, they're vibrating because they want to move. You know, think about on days when, if you've ever seen like somebody who has a ton of energy, but they just have to sit down. They're kind of sitting there and they're moving as much as they can within that little space that they're allowed to move. That's kind of how particles are. So like think about in your desk, it's a solid, you know, if you hit it with your hand, it's going to hurt. It's very solid as you well know. But understand that the particles in there are vibrating right away. They're always moving. Now, a solid, that is one of our states of matter. Solid, the definition is that it has its own definite shape and volume. Definite shape and volume. Those are the two things you need to remember. The particles in a solid are very tightly packed together. When you heat up a solid, it does expand, but not a lot. Think of think of a lid on a jar. If you're having trouble, if it's a metal lid on a glass jar, if you're having trouble getting that lid off, what do? You put it under hot water for a second. That lid, that metal will expand just a tiny bit. You're not going to be able to see it, but you'll definitely know it expanded because when you go to take that lid off, it's much, much easier. Now, the glass, okay, there are questions about whether glass is solid or liquid, but the glass is not going to be expanding as much as the metal, so it does make that lid easier to get off. And solids are incompressible. That means that if you have a solid, like a rock or something, then you can't fit the same amount of particles into a smaller space. That's the whole point. They're solid. They can't get any. You can't tight them. You can't fit them into a tighter suitcase. Here's an example of a solid. I like art, so I'm going to show you some art. This is a marble statue or sculpture, and that is definitely solid, as opposed to these two examples, which are wax. This is another sculpture, but it is made out of wax instead of marble, and you guys know that's a candle right there. Here, I'm going to point at it. Boom, candle. All right, what's the difference, and why do I need to show you? Because you know that wax is a solid, and you know that marble statue was a solid. So why am I pointing this out? Just understand that when you're looking at a solid, it's not defined by how hard it is or how rigid it is, or whether or not you can mush it with your hands or sculpt it essentially, or if you hit it with your hand, you're going to break your hand. That's not the definition. That's not how we determine whether or not it's solid. So it can be soft like wax, but it's still a solid. Remember, it's the particles. Do the particles have a definite shape? Yes. Okay, you're halfway there. Do they have a definite volume? Yes. All right, now you're a solid. Our second state of matter that we're going to study are liquids. what's the difference between a solid and a liquid? Well, let's look at it for a second. A liquid flows. A solid does not. A liquid has a constant volume. That means that it's not going to change. The liquid's volume is not going to change. Remember, a solid's volume was definite. It doesn't change either. The difference is in the shape. Remember, a solid had a definite shape. The liquid does not. The liquid takes up the shape of the container. So let me go to my handy dandy writing. So solid, you have definite shape. Yes. You have a definite volume. Yes. A liquid, you have a definite shape. No. And do you have a definite volume? Yes. There's the difference right there. So, let's see here. In a liquid, another difference is that the particles are not as closely packed in as in a solid. They're near each other, but they're not shoulder to shoulder, and so they can slide past one another. And it's virtually incompressible. A liquid is virtually incompressible. Can you compress it a little bit? For all intents and purposes, the amount that you can compress most liquids is negligible, meaning almost non-existent. So we say that it's virtually incompressible. So if you have a yes/no question, is a liquid compressible? Your answer would be no. And we know that because of hydraulics. We use hydraulics, and if you don't know about hydraulics, look them up. They're kind of fun to look at. But a hydraulic is a tube. Let's go pink on this one. A hydraulic is a tube filled with a liquid. What happens is, and I guess it comes around to this side. There's another tube filled with another liquid. All right, what happens is you put force down on this side. The fact that the liquid is incompressible creates pressure, and it sends this side up. So it allows you to use a very small amount of force to lift heavy objects, which is really cool. Hydraulics are used all over the place in mechanical worlds where it's time to lift something heavy. Your brakes, your airplanes use them. All right, listen, just look it up. Hydraulics are really cool, and the only reason we can use them is because of the virtual incompressibility of liquids. And when you heat up a liquid, it does tend to expand, at least a lot more than a solid does. What's a huge example of something that does not expand when you heat it, or something that actually, remember I said that a solid expands slightly when you heat it, and a liquid expands more when you heat it. There is a great example of something out there. It's very common, and when you freeze it, it gets bigger, which is what you would not expect to happen. And when you heat it, it gets smaller, which again is the opposite of what you would expect to happen. So, so go out there, do a little bit of research. This is your first note check, and come back and tell me what substance is it that I'm talking about that does that. Here's a picture of a liquid taking the shape of the container in which it flows. So, look at your water bottle. The liquid inside has taken the shape of the bottle. If you pour it out into the room, it'll do the absolute best it can to take the shape of the room until, of course, it runs out of liquid. So then it'll puddle. That's a huge difference between a liquid and a gas, is the fact that the liquid will puddle. It wants to stay. Here, this is a beautiful picture of a puddle or a cloud or something else, maybe a roller coaster. And but this is the difference between a gas and a liquid, is that the particles here do want to stay together. They're still together, but they're still going to do the best they can to take the shape of the container until, of course, they run out of particles. So you guys understand that, because if you have a glass, here's a glass, and you fill it up with liquid, just like that, boom, liquid going in, it's not going to take the entire shape of the container. It'll only take up as much as you have liquid. All right, and if you pour that out, it'll go down there and it'll puddle. I think you understand. Don't lose sight of the fact that anything can be a solid, a liquid, or a gas. There are metals that are liquids in natural, at room temperature. Here's one. What is that? You tell me. You still tell me. We haven't learned those yet. So you tell me, what metal is that? Note check number 2. And please, I'm going to run out. I'm not going to remember what number the next one is, so don't make me. There's another metal out there that is not a liquid at room temperature, but it's really, really close to it. It's called gallium, and that it's a lot of fun to play with. It's very similar to this metal, which I'm not allowed to tell you what it is because you're supposed to tell me. But gallium, when it at room temperature, it's solid, but you put it in your hand for a few moments, and it'll melt and look just like this. And so you can play with it, put it down on the desk, it'll solidify again, pick it up, and it will liquefy again. And in the past, scientists and chemists have had fun tricking each other, giving each other like teaspoons and coffee spoons made out of gallium. And so when they go to stir their hot coffee or hot tea, the spoon just disappears. Now, hopefully those scientists and chemists are smart enough to know not to drink the liquid that's left over. So that's one of those pranks where you could actually hurt somebody. Don't do it. Here's a pretty picture to show that particles are not rigidly held in place. Notice they want to stay together. Here, I'll draw a little picture. Like these particles are wanting to stay together, but they're not held in place. They're able to flow, they're able to move. Listen, this is just a pretty picture I wanted to show you. Here's another pretty picture. In case you're wondering what in the world this is, I thought it was obvious, but in the past I've had students ask, what are these? Are they spaceships? No, they're not spaceships. They're drops of, I believe, milk in water, or something like that. And then all the pretty colors were added in Photoshop afterwards. Now on to the third state of matter that we're going to study. It's really the last one that you're responsible for, but I am going to go on to the next one here in just a few moments because people love it. Gases flow to conform the shape of their containers. Let me get out my little thing here. They flow to conform to the shape of their containers, and here's really the important word, the one I didn't highlight or bold, and that is completely. Remember, a liquid will fill it up as much as it can until it runs out of space or runs out of liquid, and then the rest of it is not full because, again, these particles, they want to stick together. A gas, on the other hand, you fill it up with a gas, and those particles have a field day. They're like, I want to get away from you, and so they fill up the container completely, and they just bounce around, and it's like a little fun bouncy house with a bunch of little kids. In a gas, the particles are very far apart. Look. All right, here. In a liquid, see, they're much closer together, and I'm not even trying to draw a solid because those are already too close. But they're closer together in the liquid. They want to stick together. In a gas, they're like, get away from me. I need my space. They're like kindergartners on a whole lot of sugar. So they're just bouncing off the walls. So I do think of gases as the particles being you get a bunch of kindergartners in a little room and just watch them go, and they're gonna go until they here's a kindergartner and. They're just so happy, and they're just running around, crazy kindergartner. And that kindergartner is going to run until it runs into another happy kindergartner. There it goes. And once it hits that, it's just going to bang and bounce off and go the other direction until it hits a wall over here. Bang, and it's going to bounce off and do that. The only difference between a kindergartner and a particle is that particles can go in 3 dimensions. Kindergartners, the only time you see them go in a 3rd dimension is when they land on their faces. Boom, like that. And then they cry. And we don't want that. So, those are big tears. Okay, so that's how I think of gases. So now you know what goes on inside my head. Gases are easily compressible. That means that the same number of particles, you can fit those into a smaller container. I'm not going to try to redraw the exact same number of particles, but you can take all the particles in this picture right here and fit them into a much smaller container. Remember, solids can't do that. Solids are not compressible. Liquids, I'm going to run out of space, are not compressible, virtually incompressible. Gases, oh, it's right there, are totally compressible. And we love the fact that we can compress gases, that we can put them in smaller spaces. How do you use them? Well, how about a car jack, a pneumatic jack, as long as it's not hydraulic. Remember, hydraulic jacks use liquid. Pneumatic jacks use air. And so, again, you can use the compressibility of gases to lift heavy objects, the exact same concept. You just compress it until it can't be compressed anymore. And it allows you to create force in another direction. That's physics. Let's worry about that later, and by that I mean next year. Another way that we use gases to compress is, how do you get air into your tires? Well, you use compressed gas. How do you clean off your keyboard? Well, I just turn it over and hit it. But most people use compressed gas. And then finally, you've got scuba tanks. If we didn't have scuba tanks, that doesn't look like a scuba tank at all. So here we go. Scuba tank. Pretend with me that that's a scuba tank. Then now we're able to breathe underwater, or at least, go underwater for long periods of time with compressed oxygen. You take all the oxygen that would normally be in a room and you can fit it in a tiny little scuba tank and have at it and play with the little fishies and, a shark and all that junk. Another way is, this looks more like an aerosol can. Boom, compressed air is allowing you to squirt that easy cheese into your mouth. Yum. So I said that one of the properties of gases is that they flow to fill up their containers completely. Here you can see that happening. I like to show you examples. Here you can see that is a gas flowing. The smoke allows us to see how it flows. Isn't it pretty? Yes, don't smoke. And here you can see that the gas is taking up the entire container. If this were a beautiful purple liquid called Kool-Aid, then it would only go that far, right? And they would all be together. Here, think of them, they're little purple kindergartners, like little Barney dinosaur kindergartners. Ugh. All right, there it is. Easily compressible, so you take all the air in the room, well, it would be oxygen, and you can stuff it into this container, you can stuff it into a smaller container, that container, actually it's less air, but it's all compressed, so you can get a bunch of air into a little tiny container, which allows us to go places like into fires, underwater, etc. Is air being compressed into that? No, it has to be airtight. You knew that. Here are gases out in nature. This is yellow. They're in a volcano, I believe. They're not actually in the volcano, but they're in the cone of the volcano. If they were in the volcano, it might be a little too warm for them. They might be melting, which is a phase change, by the way. Look, you're always learning. Can you tell me, based on the physical properties that you're seeing here, the intensive physical properties, what you think this substance might be? I'll give you a hint. Hold on, here it comes. I'll give you a hint. Ew, here we go. Stinky. All right. There we go. And so this is a gas that's coming out, it's venting out of a volcano. And so, yeah, so is this number 3 on your note check? I don't know, but it's still a note check. Come tell me. I enjoy learning about gases and their electrons, when you excite their electrons, and we're going to learn all about that, and it's going to be fun. But when you excite the electrons of a gas, you can create light. And based on what kind of gas you're using, you can create different colored lights. Remember, different elements create different flames, different colored flames when you flame them. Same concept here, but now we're creating light that doesn't just go away once it's used up, because, well, we'll get into that much later. So, neon lights, yay, fun. You're used to gases being colorless. Well, just like in the cartoons, not all gases are colorless. Here we've got chlorine gas. This is very toxic. Ask me to tell you about chlorine gas and how it shaped the world into what we know today, because it's a really interesting story, but nobody's got the bandwidth for that. So stay away from that. I like to tell you, it'll kill you hard. This is a bromine gas, and bromine gas naturally comes in this hideous color that looks like it will kill you. So apply, same thing. Chlorine gas will kill you hard. This will kill you hard as well, but not quite as hard, but still, you're still dead. So let's stay away from that. Pretty much if you can see a gas with a color, you might want to walk away. You might want to stop breathing and walk away, and then breathe when you get to good air. All right, and then here we've got a purple gas. What's that? That is iodine. When iodine becomes a gas, it is beautiful violet purple. But if you look at it, it still looks a little dangerous. Is it? What I just tell you, if you can see a colored gas, walk away. Yeah, it's dangerous. People ask all the time. Maybe they don't. Maybe they do. I don't know. People don't really ask me all the time. But if they thought about it, they would. What's the difference between a gas and a vapor? Let me tell you. A gas is naturally in the gaseous state, at room temperature. So think about it this way. At room temperature, which for me is very warm, for you is about 72, 73 degrees, if it's naturally a gas at that room temperature, it is a gas. If it is naturally a solid or a liquid at room temperature, then when you put it into the gaseous state, then it is not a gas. Technically, you would call it a vapor. So a vapor is a gaseous state of a substance that is a solid or a liquid at room temperature. And that's how you know. Water, for instance, well, hold on a second. I think the next slide will show you that. Ba-bam, I didn't lie. Water, for instance, is liquid at room temperature. H2O is a chemical, and it is liquid at room temperature. So when you turn it into the gaseous state, that's a phase of matter or state of matter, then it is not a liquid, it is not a gas, it is a vapor. Here you can see it. That's called the Tyndall effect, where you can see the particles because of the light coming through. Here you can see this is a jet making himself a little sonic boom. And that creates instant condensation right there. He made his own little cloud. And here are clouds as well. Those are little tiny particles of water up in the air because well, I'm not going to explain weather to you. That's a whole nother class. But those are little tiny particles of water, and you can see them right there, but they're in the gaseous state. If they weren't, it would be raining. Then they would be in the liquid state. And then if it's cold enough on the ground, on Highway 67 right here, it would be ice, and you would be slipping, and this is you after ice. Wah, like that. Oh, because you fell on your bum right there. All right, it hurts. Don't do that. Anyway, that's the solid phase of water. And so anyway, point being that this was a liquid at room temperature. Now it's a vapor, if you want to be technically correct. Now, am I going to count you off if you call it a gas? Only if it's on a test, and I'm specifically asking you about that. Here's a nice comparison, somebody else drew it, not me, of the states of matter. This is what you need to be able to draw. This is what you need to be able to know. Let's start down here. A solid. Look at the particles. They're tightly packed together. They're shoulder to shoulder. You stick those kindergartners with all that sugar into a room that's really, really, okay, let's put them in a closet, but let's not turn off the light because that'll scare them. Let's put them into a closet. They're shoulder to shoulder, or an elevator. How about that? That's not as scary. You put them into an elevator. They're shoulder to shoulder. They're still on sugar, so they want to move. So they're going to be, vibrating around, but they can't move. So basically, they're just hitting each other, jostling each other, and there they are. So there's still action right here, but they can't go anywhere. Definite shape, yes. That shape does not change. That's a check mark. There we go. Definite volume, yes. That volume does not change. Is it compressible? No, it is not compressible. You cannot fit that into a smaller container. All right, let's look at liquids. I'll change color. And liquids, the particles are not as tightly packed in together. They can flow past one another, but they're still they still run into each other pretty often. So think about it this way. You take a kindergartner on the first day of school. They're going to stick with, put them in kind of the lobby, and they're going to kind of stick with their mom and dad or the friends that they know. They're not going to get away from them, and, safety in numbers. And so they're wanting to touch everybody, but they're not running away wildly yet. You haven't let them out into the big room to play yet. Do these have a definite shape? No. Do they have a definite volume? Yes. And are they compressible? No. So liquids, that's what you need to know. I'm sure that these are not helpful because there are no words right there. But you know what? Work with me. All right, gases, on the other hand. Gases, you've just let your kindergartners on sugar out into a huge room. Oh, they're just going to go wild. They're going to run. They're going to play. They're going to bounce off of things, each other. There's going to be crying. There's going to be peeing in their pants. It's going to be wild. And is it going to be fun for you? No, you have to take care of that and probably clean everything up. But they're having a blast, and that's what a gas is just like. So here you go, gas. Definite shape? No, it fills up the shape of the container completely. Definite volume? No, because you can change the volume of how much you have. And is it compressible? Absolutely, it's compressible. That's the whole point of a definite volume, or lack thereof. All right, let's talk about energy really quickly in relation to solids, liquids, and gases. You know that if you take water and you solidify it, it's cold, right? In order to get it to be a liquid, you have to heat it up. And so liquid at room temperature, it's not cold anymore. It's not hot, whatever. If you heat it up a lot more, it'll turn into a gas or a vapor. So relative energy. I've been talking about our little kindergartners in a room. What's actually happening is our kindergartners here are not really on a lot of sugar. They're packed in together. What happens when you put kindergartners packed in together? They eventually will settle down after they stop crying. They'll eventually settle down and kind of nap. Are they still moving? Yes, their little chests are going up and down because they're breathing. So they're still moving, but there's not a lot of movement. They're napping. Here in a liquid, the heat has gone up. Therefore, the energy is going up as well. They're going to move around. They're talking to their moms. They're crying. I don't know why I think kindergartners cry so much, but they do. That's why. So they're talking to their moms and dads. They're saying hi to their friends, but they're not going crazy yet. Here, it's not the first day of school anymore. They know all their friends. You let them into school, and they're just crazy wild. Remember, we've just given them sugar. They're running around wildly, and so particle-wise, this has a lot more energy. Gas has a lot more energy than liquid. Liquid has a lot more energy than solid. Everything's still moving in all of them. It's just, the amount of heat and or pressure has changed so that that affects the amount of energy that the particles are experiencing. Here's the other state of matter, the fourth state of matter, plasma. Plasma is a lot of fun. Plasma is matter consisting of positively and negatively charged particles, but the overall charge is neutral. Your book doesn't cover this. It's complicated. You want to learn more about plasma, go to school or look it up. And by school, I mean college. You're in school. So, look it up. It's really interesting. Plasma is a lot of fun. And by a lot of fun, I mean it is a lot of fun. Here is a picture of plasma. Ooh, pretty. I have a plasma ball in the room. Maybe by the time you get into class today, I'll have plugged it in for you so you can come look at plasma and play with it. And by play with it, I mean while it's encased in a jar because you don't want to get electrocuted. Here's another example of plasma. Who's that dude right there? Who is that? Who's that good-looking ball of gas? Plasma right there. That's right, that's our sun. Next time you call any star or the sun a big ball of gas, are you right? No, you're wrong. It's a big ball of plasma. Now you can get it right. And here is the most common form of plasma that you're actually going to witness on a regular basis, especially in these areas in the spring, summer, fall, and sometimes the winter as well. And that is lightning. That's plasma. You thought it was electricity, didn't you? Well, it's electricity moving through the particles. That's plasma. So there you have it. Plasma. Your book doesn't cover these either, but I think they're an absolute blast. They're weirdos. They are called, this is, here, let me tell you how to pronounce this. This is amorphous solids and liquid crystals. An amorphous solid, what does that mean? A meaning not, morph meaning shape, us meaning pertaining to, so it's pertaining to, I think it means, I don't know. So it's pertaining to not having a definite shape. And that's a solid. It's a solid that does not have a definite shape. What? Didn't we just learn that a solid, that's the definition of it, that it has, well, half a definition, it has a definite shape. So what's an amorphous solid? Think of your GAC and Newtonian, what they call Newtonian liquids. So just go look it up. There's a bunch of them. They're a lot of fun. Anything that looks like a solid, acts like a solid, but then when you stop putting force on it, it starts acting like a liquid. These, like I said, they're weirdos. You're not responsible for them, but why do I talk about them? Because they're fun to play with. And are we going to play with them in a lab? Heck yeah. Why else would I bring them up? Liquid crystals, you guys work with those on a regular basis. Every time you use your calculator, you're using liquid crystals. Liquid crystals are really cool. Okay, so they're liquids, but when you throw some electricity through them, all of a sudden they start acting like solids. You can shape them. sorry about that, you can shape them and you can control what you do with them, or what shape they go into, which is how we get LCD screens, liquid crystal display, LCD screens. So anytime you see something with those little black numbers, like on a calculator or the older watches, anytime you see that with like, not the red ones, that's something else, then that's a liquid crystal display, and now you know that it's liquid, but when you throw electricity through it, they turn rigid, and so you can control them. I think I just already said that. So let's see if you were paying attention. This is note check number 4. And why do scuba divers use compressed oxygen? Show me the answer. Here's the answer to last lesson's question, which is the most common state of matter in the universe. Now that you know that stars are not big balls of gas, but they're big balls of plasma, then now you know that the most common state of matter in the universe is, in fact, plasma. Because all those stars are gigantic, and they are all plasma. They're not made of plasma. They're made of whatever they're made of, hydrogen, oxygen, nitrogen, etc. The state of matter is plasma. Please don't get that confused. Ask me in class to show you guys my video of the relative size of stars. It is mind-boggling. And that brings us to the end of this lecture. So, yay, you're free. Here, I'm going to draw the little kindergartner. Yay! Kindergartner's going to go run wildly, and y'all can go play with the kindergartner now. Wait, I forgot something. You are not released from this lecture yet. All right. Remember earlier I referred to other state of matter, right? If the other state of matter is plasma, there's other state of matter, a fifth state of matter. All right, go do some research, come back and tell me. This is your final note check. I have no idea what number it is. So go back, do some research, and come and tell me what is that last state of matter. The cool thing is it's the only state of matter that as far as we know, it's only man-made, so whatever. Go find it and tell me. Learn something on your own. Yay. Oh, now you're released. Go play with that kindergartner. But be nice. Don't make it cry.